morning, everyone, and thank you for being here while we share with you our exciting new results about our galaxy, the Milky Way. Our home in this universe, what fills our night sky on a dark summer night. At its heart, towards the constellation Sagittarius, is Sagittarius A star, the supermassive black hole suspected to reside there. A source that has been a focus of intense astronomical studies for decades. Observations of stars orbiting around it revealed the presence of an object that is very massive, 4 million times the mass of our sun, but also very faint. For me personally, I met it 20 years ago and have loved it and tried to understand it since. But until now, we didn't have the direct picture confirming that Sag A star was indeed a black hole. Today, the Event Horizon Telescope is delighted to share with you the first direct image of the gentle giant in the center of our galaxy, Sagittarius A star. This image shows a bright ring surrounding the darkness, the telltale sign of the shadow of the black hole. Light escaping from the hot gas swirling around the black hole appears to us as the bright ring. Light that is too close to the black hole, close enough to be swallowed by it, eventually crosses its horizon and leaves behind just a dark void in the center. Getting to this image wasn't an easy journey. It was one of building a worldwide telescope array and a global collaboration. One of getting and processing petabytes of data collected from those telescopes. Of imaging algorithms more complex than many that have ever been developed. What made it extra challenging was the dynamic environment of Sag A star, a source that burbled and gurgled as we looked at it. And the challenges of looking not only... something is advancing the slides without... Can you please go back to the earlier slides? What made it extra challenging was the dynamic environment of Sag A star, a source that burbled and gurgled as we looked at it. And the challenges of looking not only through our own atmosphere, but also through the gas clouds in the disk of our galaxy towards the center. It took several years to refine our image and confirm what we had, but we prevailed. The HT collaboration has indeed been hard at work, imaging black holes with exquisite resolution using new techniques. In 2019, we revealed the very first such image, that of the supermassive black hole in the M87 galaxy. That black hole is 1,500 times more massive, making its horizon 1,500 times larger. But it is also 2,000 times further away from us. This makes the two images appear very similar to us when we gaze at them in the sky. But the two black holes couldn't have been different from each other in practically every other way. The one in M87 is accumulating matter at a significantly faster rate than Sag A star. But perhaps more importantly, the one in M87 launches a powerful jet that extends as far as the edge of that galaxy. Our black hole does not. And yet, when we look at the heart of each black hole, we find a bright ring surrounding the black hole shadow. It seems that black holes like donuts.
Imaging a black hole is a task that's too big for one individual or a single observatory. As we found out the first time around, it's a lot of work. Large teams of people have to pull together to handle the science, engineering, and operations. It also requires many telescopes. To distinguish the ring-like structure in Sagittarius star, our telescope had to be almost as big as the Earth. Fortunately, the technique of interferometry allows us to link pairs of telescopes that are very far apart into the equivalent of a planet-sized telescope. We use this technique both for Sagittarius star and the black hole in M87, or M87 star as it's called. But these two black holes are quite different from each other, as Ferial described. And for reasons Katie and Michael will explain, imaging Sagittarius star turns out to be a lot harder. Today's results come from the same 2017 observing run as M87 star, but with a big difference. The South Pole Telescope at NSF's Amundsen-Scott South Pole Station observed Sagittarius star, whereas M87 star was completely out of view. So while we had 7, all 8 could see Sagittarius star. The South Pole Telescope is perfectly suited to observe Sagittarius star, both because it can see it continuously and because it significantly increases the resolution of the array. In interferometry, each radio telescope is at a different location. By correlating their signals and studying resulting data, we can reconstruct images of the source. The more telescopes, the better. The farther apart they are, the more we can zoom in on the source. Turning pairs of telescopes into the nodes of an interferometer is a process similar to everyone shaking hands with everyone else in a room. You need at least 2 people, and the number of handshakes grows very quickly as you add more people to the group. So the amount of data we get also grows very quickly with each telescope we add to the EHT. When we observed Sagittarius star, 8 telescopes collected around 3.5 petabytes of data. That's equivalent to about 100 million TikTok videos. It's way too much data to stream over the internet. We actually have to ship hard drives around. But just gathering the data isn't enough. The data has to be carefully combined, calibrated, and converted into an image, with teams of scientists, many of them right here in this room, working on each stage of the process. After the observing sessions, teams from each site ship hundreds of hard drives back to the correlation centers in Westford, Massachusetts and Bonn, Germany, where supercomputers combine the signals and produce raw input data. The calibration team combines the raw data with information about the sensitivity of each telescope to form the data used by the imaging teams. And then the imaging teams process the information using a variety of methods to reconstruct the best possible images of the hot plasma surrounding the black hole. Other teams then extract features from the image, and so other teams run massive simulations based on prior physics studies that predict how material behaves around black holes on the scale of Sagittarius star. Coordinating all those intensive efforts to image M87 star was already incredibly difficult, and the global pandemic emerged right as we pivoted to Sagittarius star. The pandemic slowed us down, but it couldn't stop us. Our collaboration meetings and workshops were moved fully online, but there's no substitute for getting together in the same room and working through hard problems. But Sagittarius star brought a number of new specific challenges, even though it is closer to Earth. First, M87 star doesn't change very quickly, but Sagittarius star does. In this sequence of model images, 1 second is equivalent to almost 2 days. Imaging a rapidly spinning turbulent source like Sagittarius star is a lot harder than it was for M87 star. As Katie will describe, material swirls around M87 star over the course of many days, but it takes only a few minutes for material to move around close to the horizon of Sagittarius star because it is much smaller. It changes quickly, so we had to collect our data quickly. To further complicate things, we see Sagittarius star through an enormous amount of material in our own galaxy, which scatters the radio waves and blurs the image. But years of observations at other wavelengths have made it possible for astronomers to partially mitigate the effects of this blurring. The result is an image that, until we finished our analyses, we were never sure we could get. Our collaboration's remarkable image of Sagittarius star and our scientific conclusions were a combined effort that involved not just the handful of us on stages around the world today, but more than 300 people all working together, united by our fascination with black holes. We are especially grateful for our students, postdoctoral researchers, and early career scientists who worked very long hours to produce these results. Yet the EHT collaboration does not operate alone. As detailed in our 6 papers, we work together with other teams of astronomers observing signals across the electromagnetic spectrum, from radio waves to infrared and X-rays, all of which provide us with important context to understand the image. Our results build upon decades of studies by other groups that establish that Sagittarius star contains a dark, massive object, characterized its properties, and retained accurate measurements of its mass and distance. We especially want to recognize the hard work by Nobel laureates Andrea Ghez and Reinhard Genzel and their teams studying the orbits of stars around the galactic center. Some scientific results are the work of small teams. Imaging Sagittarius star took an entire planet. And now I'd like to introduce Katie Bauman of Caltech, who will talk about how we captured this black hole image.
Today, we are thrilled to reveal the very first image of the supermassive black hole at the heart of our own Milky Way galaxy. This image from the Event Horizon Telescope required more than just snapping a photo from telescopes at high mountaintops. It is the product of both technically challenging telescope observations and innovative computational algorithms. Taking this picture proved even more challenging than imaging the M87 black hole, which we revealed to the world back in 2019. To understand why, let's go back to how our telescope works. As Vincent mentioned, the EHT doesn't work like a regular telescope. Instead, our radio telescope shakes hands. They work in pairs, with each pair contributing a little bit of information to the entire image. Telescopes that are far apart can detect the smallest, sharpest features of the image. Orientation is also important, with each angle picking up different parts of the whole. Telescopes that are closer together become sensitive to the broad features of the image that the wider pairs can't see. And combined, these components of the image can provide a good representation for the target we're observing. Making a perfect image would require telescopes at all different orientations and separations. But EHT's 8 telescopes scattered around the globe only capture some of these potential pairings. Luckily, as Earth rotates, the projected separations and orientations between the telescopes change, providing more, but not all of the information we need to make a perfect picture. As Michael likes to say, taking a picture with the EHT is a bit like listening to a song being played on a piano that has a lot of missing keys. Since we don't know when the missing keys should be hit, there's an endless number of possible tunes that could be playing. Nonetheless, with enough functioning keys, our brains can often fill in the gaps to recognize the song correctly. This was also the case for imaging M87 star. But for Sagittarius star, there was another daunting challenge that we couldn't ignore. The hot gas spiraling around these 2 black holes moves at roughly the same speed. But where gas takes days to weeks to orbit the much larger M87 star, for Sagittarius star, because it's a lot smaller, gas can make a full orbit around its event horizon in mere minutes. And that means as we were collecting data during the Earth's rotation, the material was swirling around Sagittarius star so quickly that Sagittarius star's appearance could change from minute to minute. This is a bit like changing the key of the song as we are playing it on our broken piano. We had to address all those challenges, along with many other challenges that I don't even have time to get into, like the fact that we're observing the black hole through Earth's turbulent atmosphere, as well as the galaxy's gas. And to tackle these challenges, we spent years developing computational imaging algorithms that allowed us to recover a picture of the center of the Milky Way with the collected incomplete data. But the question remained of how do we fill in that missing information? To capture the range of potential Sagittarius star appearances, our team produced tens of thousands of different images with different methods that filled that information in differently. Each of these images is slightly different, but they are all consistent with the EHT data. By averaging these images together, we're able to emphasize the common features appearing in most of them. And here, a bright ring clearly pops out. But it's important to note that not all the images that we recovered looked alike. In fact, we found that we could cluster the recovered images into 4 categories based on similar visual features. 3 of the clusters contained a ring-like feature with only differing brightness around the ring. However, there existed a much smaller 4th cluster that contained a variety of images that did not appear ring-like. Although these non-ring images couldn't be fully ruled out from the data alone, the vast majority of the images that our algorithms recovered had a ring shape. And through literally years of exhaustive tests on both real and simulated data, we're now confident that there is compelling evidence that the true underlying structure is a ring. A detailed analysis of the images has revealed that they all share the same ring size, a size in perfect agreement with prior observations in theory. 50 microarcseconds, or in other words, a size 1/13 billionth the span of our night sky. Coming to this conclusion took years, but we never backed away from the challenge. And through the power of computational imaging, the EHT team overcame seemingly impossible hurdles to capture the first image of the beastly black hole at the heart of our galaxy.